In this section 4.4, we're going to take a look at exponential and logarithmic equations. There are different objectives we would like to cover. The first one is that we're going to use like bases to solve exponential equations. Then we're going to use logarithms to solve exponential equations. Then we're going to use a definition of a logarithm to solve logarithmic equations, rewriting a logarithmic expression as an exponential one, or remember that in this situation you could also use the technique of zapping the log. You can zap the log. Okay, and the last objective we would like to take a look at is using the one-to-one property of logarithms to solve logarithmic equations. Let's take a look at the first one, which is to use like bases to solve exponential equations. So if we had the following, if we wanted to solve exponential equations by expressing each side as a power of the same base, we could use the following property that we have here. If you have b, the base b raised to the power m equal to the base b, the same base, notice, raised to the power n. If you have the same base b on both sides, then it means that the exponents have to be a match. So it means that m would have to be equal to n. So the idea is to either look at your equation and notice that it's already in this format as b to the m is equal to b to the n, or if it's not, you would have to rewrite it in this format of, having the same base on both sides, base b. Now, once you have done that, the next step is to go ahead and, since the bases are the same, you have the base b on both sides, then your next step would be to go ahead and match the exponents and say that m is equal to n. And then once you have that next step, you're going to solve for the variable that is involved in this equation. So let's take a look at an example. Let's say we want to solve 5 to the power 3x minus 6 is equal to 125. So notice that 125 is 5 times 25, which is 5 times 5. So 125 is 5 times 5 times 5, which is 5 to the third power, which you may know already. So what we do, since we have a 5 on the left-hand side, we're going to rewrite 125 as, let's use the same base 5 on both sides, 5 to the third power. So we're just rewriting the right-hand side. Now, because we have the same base on both sides, which is 5, if the base is the same, then it means that the exponents have to be a match. So that's our next step, to go ahead and say that 3x minus 6 is equal to 3. Add a 6 to both sides, and then you get that 3x is 9, divide by 3, and x is 3. Now, before you conclude that the solution set is indeed that answer 3 that you did get right here, before you do that, sorry, the other problem is coming too quickly. Before we go ahead and say that, we should technically go ahead and check that both sides are matching if we were to replace x by 3 in the original equation. So let's go ahead and try that. So what was my original equation? My original equation is the first line that we ever read. So let's see. If we have 5 to the power 3x minus 6, is that 125? That's my question. If x is replaced by 3. So it's 5 to the power 3 times, and x is replaced by 3. So 5 to the power 3 times 3 is 9. Take away 6, that's 5 to the third. Is 5 to the third, is that 125? That's what we're wondering. Yes, it is, because 5 times 5 is 25 times another 5 is 125. So this is indeed checking out. So it is okay to take our solution and place it within braces to show our solution set. So this equation was not too bad because, we didn't have many steps to have on both sides the same base, being in this case 5, and then making the two exponents equal to each other and solving for the variable. Let's go ahead and take a look at an example of such a problem, this time from the textbook. So let's go ahead and take a look at problem 16 in this particular set of problems. So in number 16, we do have the following question. We want to solve for x so that we can have this equation be satisfied. 7 raised to the power x minus 2 over 6 equal to square root of 7. Now the question says solve each exponential equation by expressing each side as a power of the same base and equating exponents. So they really want us to use that little property we just saw, that if b to the power m is equal to the same b to the power n, if the base is the same and it happens to be, let's say b in this situation, then it means that the exponents would have to be a match. Then you would get that m is equal to n, and you would solve for your variable. So notice that on the left hand side, we notice that the base is 7. That is very obvious. So we'll keep it this way on the left. Now on the right hand side, we do want to write square root of 7 as 7 raised to a power. So let's work on this a little bit on the side so we can see what to write on the right hand side. So let me do some scratch work here. On that page, if we have the following, let's remember, if you have the nth root of, let's say, a, it is a to the power 1 over, and then what you do is the following. Whatever this index of the radical, whatever it is, you're going to place it underneath the fraction bar here. So the nth root of a is a raised to the power 1 over n. So having said that, if you had square root of 7, let's remember that it's really over here when we say square root, we have a little 2 here as the index of the radical, which we don't bother mentioning since it's so common. And that's the same as writing 7 to the power 1 over, and then grabbing this 2 that we emphasized and placing it underneath. So it's 7 to the power 1 half. So square root of 7 is 7 to the power 1 half. So let's rewrite square root of 7 as 7 to the power 1 half. And I'll do that on the right hand side. Square root of 7 is 7 to the power 1 half. Now, because we see that we have the same base on both sides, that is 7. So the base is 7 and it's the same base on both sides. Then it means that those exponents have to be matching as well. So we're going to solve x minus 2 over 6 equal to 1 half. Now to solve this, we can go ahead and cross multiply. Let me just write it one more time so it's not too messy. So we cross multiply. So we have that 2 times x minus 2 is equal to 6 times 1 or 6. Now let's distribute. So we have 2x minus 4 is equal to 6. Add a 4, 2x is 10, divide by 2, x is 5. And that's the answer we believe will be in the solution set. But before we say that, let's make sure that if we replace x by 5 in the original equation, that both sides are the same. So let me do my little check over here. So if we check before concluding, and we have 7 to the power again x minus 2 over 6, is that the square root of 7? Let's replace x by 5. So we are asking ourselves, is 7 to the power, where x is replaced by 5. So 7 to the power 5 minus 2 over 6. So that's 7 to the power 3/6, which is really 7 to the power 1/2. We're wondering, is that square root of 7? Yes, indeed it is, because remember, when we say a quantity to the power 1 over something, it is the nth root, in this case the square root of over here the number 7. So it is indeed the same thing as writing just plain square root of 7 without mentioning the index of the radical. So both sides do work out, they are matching. So the solution set is indeed the number 5. Now you could use this technique on any base. Let's say we had to solve the exponential equation with base e, and it's number 22 here. E to the power x plus 4 is equal to 1 over e to the power 2x. What we need to notice over here is that on the left we have e to a power. So we're going to use the base e on the other side. And how we're going to write the other side as e to some power, just realize that when you have something in the denominator of a quotient or in the numerator, you can always send it up or down, provided you change the sign of the exponent. So in the denominator, we had e to the power plus 2x. So when you send it up, it would be e to the power negative 2x. It's opposite. So that's what we're going to use. So now we're going to say, since the base is the same, it's e, then the exponents should be matching, and we would have that x plus 4 should be equal to negative 2x. Now let's solve for x by adding a 2x to both sides. So we have 3x plus 4 equal to 0. Now subtract a 4, and we have 3x is negative 4. Divide by 3, and we have that x is negative 4/3. And the solution set is going to be negative 4/3, and you should technically check that both sides are matching by replacing x by negative 4/3 here and there as well. Now let's take a look at the following. If we wanted to check that this equation is satisfied by the solution that we got, remember the following. Notice that our equation is next to the number 22, we read e to the power x plus 4 is equal to 1 over e to the power 2x. And if we think that x is negative 4/3, we should replace x by negative 4/3 like I'm doing on the check on the right hand side. Now if you replace x by over here, if you replace x by negative 4/3, you get this on both sides. Okay, now to clean up the exponent which is on the left, which is negative 4/3 plus 4, you can do those steps which I have right here, and you get 8/3 for the left hand side, so it's e to the power 8/3. Now for the right hand side, if you wanted to clean up what's in the denominator, if you have a 2 times a negative 4/3 as an exponent on the e base, which is in the denominator, you get 2 times negative 4/3 is negative 2 times 4/3, which is negative 8/3. But remember, that e to the power negative 8/3 is in the denominator, to send it back up, what you would do is the following. You would just remember that we have on the left hand side again e to the 8/3 is equal, and when you send this to the numerator spot, you get e to the positive 8/3. So both sides are matching. So that's how you can check that indeed your solution set is what you think.